Foot Soccer World Cup Final, Standard Platform League, is about to start. Let's go now.
It turns out what you can do is if you give this sort of data, say an image, to certain unsupervised learning algorithms, they will then learn to group pixels together and say, gee, this set of pixels seem to belong together and that set of pixels seem to belong together. And so the images you see on the bottom, I guess you can just barely see them. So the images you see on the bottom are groupings, are what the algorithm has done to group different pixels together. On a small display, it might be easier to just look at the image on the right. The two images at the bottom are two sort of identical visualizations of the same grouping of the pixels into contiguous regions. And so it turns out that this sort of clustering algorithm, this sort of unsupervised learning algorithm, which sort of learns to group pixels together, turns out to be useful for many applications in vision, in computer vision image processing. Let's show you one example. This is a rather cool one that two students, Ashutosh Saxena and Min Sun here did, which is given an image like this, right? This is actually a picture taken on Stanford campus. You can apply that sort of clustering algorithm and group the picture into regions. Yeah, let me actually blow that up so that you can see it more clearly. Okay, so in the middle you see the lines sort of grouping the image together, grouping the image into contiguous regions. And what Ashutosh and Min did was they then applied the learning algorithm to say, can we take this clustering and use it to build a model, to build a 3D model of the world. And so, using the clustering, they then had a learning algorithm try to learn what the 3D structure of the world looks like, so that they could come up with a 3D model that you can sort of fly through. Okay. By the way, many people used to think it's not possible to take a single image and build a 3D model, but able to. I'll just show you one more example. I like this because it's a picture of Stanford, of our beautiful Stanford campus. So again, taking the same sort of clustering algorithms, you can, taking the same sort of unsupervised learning algorithm, you can group the pixels into different regions, and using that as a pre-processing step, they eventually built this sort of 3D model of Stanford campus from a single picture. So you can sort of walk into the scene, look around the campus. Okay. This actually turned out to be a mix of supervised and unsupervised learning, but the unsupervised learning, the sort of clustering, was the first step. So it turns out these sorts of unsupervised clustering algorithms are actually routinely used for many different tasks. Things like organizing computing clusters, social network analysis, market segmentation. So if you're a marketer and you want to divide your market into different segments or different groups of people to market to them separately. Even for astronomical data analysis and understanding how galaxies are formed. These are just a sort of small sample of the applications of unsupervised learning algorithms, of clustering algorithms that we'll talk about later in this class. Just one particularly cool example of an unsupervised learning algorithm that I want to tell you about. And to motivate that, I'm going to tell you about consider what's called the cocktail party problem, right? Which is, imagine that you're at some cocktail party and there are lots of people standing all over. And you know how it is, right? If you're at a large party, and everyone's talking, it can be sometimes very hard to hear even the person in front of you. So imagine a large cocktail party with lots of people. So the problem is, if there are all of these people talking, can you separate out the voice of just the person you're interested in talking to, right? Because with all this loud background noise. So I should show you a specific example in a second. But here's a cocktail party that's, I guess, rather sparsely attended by just two people. But what we're going to do is we'll put two microphones in the room, okay? And so, because the microphones are just at slightly different distances to the two people, and the two people may be speaking at slightly different volumes. Each microphone will pick up an overlapping combination of these two people's voices, but they are sort of slightly different overlapping voices. So speaker 1's voice may be more loud on microphone 1, and speaker 2's voice may be louder on microphone 2, whatever. But the question is, given these microphone recordings, can you separate out the original speaker's voices? So I'm going to play you some audio clips that were collected by Taewon Lee at UCSD. Let me actually play for you the original raw microphone recordings from this cocktail party. So this is the microphone 1.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
So it's a fascinating cocktail party with people counting from 1 to 10. This is the second microphone.
1, 2, 3, 4, 5, 6, 7, 8, 9, y 10.
Okay. So remember, in unsupervised learning, we don't know what the right answer is, right? So what we're going to do is take exactly the two microphone recordings you just heard and give it to an unsupervised learning algorithm and tell the algorithm, would you please discover structure in the data for me? Or what structure is there in this data? And we actually don't know what the right answer is beginning offhand. So give this data to an unsupervised learning algorithm, and what the algorithm does in this case, it'll discover that this data can actually be explained by two independent speakers speaking at the same time, and it can further separate out the two speakers for you. So here's output 1 of the algorithm.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
And that was the second output.
1, 2, 3, 4, 5, 6, 7, 8, 9, y 10.
Okay, and so the algorithm discovers that, gee, the structure underlying the data is really that there are two sources of sound, and here they are. Show you one more example. This is this is a second different pair of microphone recordings.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
So the poor guy is now at the cocktail party where he's talking to his radio.
1, 2, 3,
There's a second recording.
5, 6, 7, 8, 9, 10.
Right. And if you give this data to the same unsupervised learning algorithm, the algorithm is actually called independent component analysis, and later in this quarter you'll see why. It then outputs the following.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
And that's the second output. Okay. So it turns out that beyond solving the cocktail party problem, this specific class of unsupervised learning algorithms are also applied to a bunch of other problems, like in text processing or understanding functional brain imaging data, like magnetoencephalography and EEG data. We'll talk about that more when we go and describe ICA, or independent component analysis algorithms, which is what you just saw. And as an aside, this algorithm I just showed you, it seems like it must be a pretty complicated algorithm, right? To take these overlapping audio streams and separate them out. It sounds like a pretty complicated thing to do. So you're going to ask, how complicated is it really to implement an algorithm like this? It turns out, if you do it in MATLAB, you can do it in one line of code. So got this from Samuel Wise at Toronto, U of Toronto, and the example I showed you actually used a more complicated ICA algorithm than this, but nonetheless, I guess this is why for this class I'm going to ask you to do most of your programming in MATLAB and Octave, because if you try to implement the same algorithm in C or Java or something, I can tell you from personal painful experience, you end up writing pages of code rather than relatively few lines of code. I should mention that it did take researchers, many years to come up with that one line of code. So this is not easy. Let me show you some fun videos of learning algorithms flying helicopters. This is a video of our helicopter at Stanford flying using a controller that was learned using a reinforcement learning algorithm. So this is done on the Stanford football field. We'll zoom out the camera in a second. So see the trees planted in the sky. So this is one of the most difficult aerobatic maneuvers flown on any helicopter under computer control. And this controller, which is very, very hard for a human to sit down and write out, was learned using one of these reinforcement learning algorithms. Just a word about that. The basic idea behind the reinforcement learning algorithm is this idea of what's called a reward function. One way to think about it is, imagine you're trying to train a dog. So every time your dog does something good, you say, good dog, and you reward the dog. Every time your dog does something bad, you go, bad dog, right? And hopefully over time, your dog will, learn to do the right things to get more of the positive rewards, to get more of the good dogs, and to get fewer of the bad dogs. So the way we teach a helicopter to fly, or any of these robots, is sort of the same thing. Every time the helicopter crashes, we go bad helicopter. And every time it does the right thing, we go good helicopter. And over time, it learns how to control itself so as to get more of these positive rewards. So reinforcement learning I think of it as a way for you to specify what you want done. So you have to specify what is a good dog and what is a bad dog behavior. And then it's up to the learning algorithm to figure out how to maximize the good dog reward signals and minimize the bad dog punishments. So just to show you, it turns out reinforcement learning is applied to other problems in robotics. It's applied to things in web crawling and so on. But it's just cool to show videos. So let me just show a bunch of them. This robot was actually, this learning algorithm was actually implemented by our head TA, Zico. Programming a four-legged dog, because Sam Schreiber in this class also working on the project, and Peter Review, and Mike, and a few others. But I guess this really is a good dog, bad dog, isn't it, since it's a robot dog. Second video on the right, some of the students, I guess Peter, Zico, Tonka, working on a robotic snake. Again, using learning algorithms to teach a snake robot to climb over obstacles. The low left, this is a kind of fun example. Artifiail 16 and Jeff Michaels use learning algorithms to teach a car how to drive at reasonably high speeds off-road, avoiding obstacles. And on the lower right, there's a robot programmed by PhD student Yirong Shen to teach sort of somewhat strangely configured robot how to get on top of an obstacle, how to get over an obstacle. Sorry, I know the video is kind of small. I hope you can sort of see it. Okay, so I think all of these are robots that I think are very difficult to hand code a controller for, but using these sorts of learning algorithms, you can in relatively short video now. Actually, could load the big screen, please. So let me play the video now. That was from Dean Pomeroy on some work he did at Carnegie Mellon on applying supervised learning to get a car to drive itself. This was his work on a vehicle known as Alvin. It was done about about 15 years ago, and it was excuse me. I think it was a very elegant example of the sorts of things you can get supervised learning algorithms to do. On the video, you hear Dean Pomeroy's voice mention an algorithm called neural networks. We'll say a little bit about that later, but the essential learning algorithm for this is something called gradient descent, which I'll actually talk about later in today's lecture. Let's watch the video.
Alvin is a system of artificial neural networks that learns to steer by watching a person drive. Alvin is designed to control the NavLab 2, a modified Army Humvee equipped with sensors, computers, and actuators for autonomous navigation experiments. The initial step in configuring Alvin is training a network to steer. During training, a person drives the vehicle while Alvin watches. Once every 2 seconds, Alvin digitizes a video image of the road ahead and records the person's steering direction. This training image is reduced in resolution to 30 by 32 pixels and provided as input to Alvin's 3-layered network.
So 2 comments, right? One is this is supervised learning because it's learning from a human driver, in which a human driver shows that, you know, if we're on this segment of the road, I would steer at this angle. If we're on this segment of the road, I would steer at this angle. And so the human provides a number of, quote, correct steering directions to the car. And then it's the job of the car to try to learn to produce more of these, you know, quote, correct steering directions that keeps the car following the road. On the monitor display up here, I'm just going to tell you a little bit about what this display means. So on the upper left, where the mouse pointer is moving, this horizontal line actually shows the human steering direction. And this, you know, white bar, or this white area here, shows that shows the steering direction chosen by the human driver by moving the steering wheel. So the human is steering a little bit to the left here, indicated by, you know, the position of this white region. This second line here, where my mouse is pointing, the second line here is the output of the learning algorithm, and where the learning algorithm currently thinks is the right steering direction. And right now, what you're seeing is the learning algorithm just at the very beginning of training, and so it actually has no idea where to steer, and so its output is sort of a white smear over the entire range of steering directions. And as the algorithm collects more examples and learns over time, you see it, you know, you see it start to more confidently choose the steering direction. So let's keep watching the video.
Using the backpropagation learning algorithm, Alvin is trained to output the same steering direction as the human driver for that image. Initially, the network steering response is random. After about 2 minutes of training, the network learns to accurately imitate the steering reactions of the human driver. This same training procedure is repeated for other road types. After the networks have been trained, the operator pushes the run switch and Alvin begins driving. 12 times per second, Alvin digitizes an image and feeds it to its neural networks. Each network, running in parallel, produces a steering direction and a measure of its confidence in its response. The steering direction from the most confident network, in this case the network trained for the one-lane road, is used to control the vehicle. Suddenly, an intersection appears ahead of the vehicle. As the vehicle approaches the intersection, the confidence of the one-lane network decreases. As it crosses the intersection and the two-lane road ahead comes into view, the confidence of the two-lane network rises. When its confidence rises, the two-lane network is selected to steer, safely guiding the vehicle into its lane on the two-lane road.
Show a video on the laptop. So let me show you a video from Yannick Kuhn on a neural network that he developed for Hamilton digit recognition. There was one other thing he did in this neural network that I'm not going to talk about, called a convolutional neural network. But well, his system is called LeNet, and let's see. I'm just trying to think, okay, how do I keep you guys entertained while we're waiting for the video to come on? Well, let me say a few more things about neural networks. So it turns out that the background, when you write out a quadratic cost function, like I wrote down on the chalkboard just now, it turns out that unlike logistic regression, that will almost always correspond to a non-convex optimization problem. And so, whereas for logistic regression, if you run gradient descent or Newton's method or whatever, you converge the global optima. This is not true for neural networks. In general, there are lots of local optima, and it's sort of a much harder optimization problem. So, neural networks, if you're sort of familiar with them and you're good at making design choices, like what learning rate to use and how many hidden units to use and so on, you can sort of get them to be fairly effective. And sort of there's sort of often ongoing debates about, is this learning algorithm better or is that learning algorithm better? The vast majority of machine learning researchers today seem to perceive support vector machines, which is what I'll talk about later, to be a much more effective off-the-shelf learning algorithm than neural networks. This point of view is contested a bit. So neural networks are not something that I personally use a lot right now. Because it's a hard optimization problem. It usually takes a while to converge. But it actually sort of works. It sort of works reasonably well. But it's just because it's fairly complicated. It's not an algorithm that I use commonly or that my friends use all the time. Oh, cool. So, but let me actually go ahead and show you an example of a neural network, which was for many years the most effective learning algorithm before support vector machines were invented. So here's Jan Kun's video, and well, there's actually audio on this too. That's not important. But so let me show you what's happening. This is what you're seeing is a trained neural network, and this display where the mouse pointer is pointing, right? This big free there is the input to the neural network. So you're showing the neural network this image, and it's trying to recognize what is this. The final answer output by the neural network is this number up here, right below where it says LearNet 5. And the neural network correctly recognizes this image as a free. And if you look to the left of this image, what's interesting about this is the display on the left portion of this is actually showing the intermediate computations of the neural network. In other words, it's showing you what are the hidden layers of the neural network computing. And so, for example, if you look at this one, the third image down from the top, this seems to be computing, certain edges in the digits, right? We're computing digits on the right-hand side of the bottom or something of the input display of the input image. Okay, so let me just play this video, and you can see some of the inputs and outputs of the neural networks, and so very different fonts. Robustness to noise. Multiple digits. That's kind of cool. All right. So, just for fun, let me show you one more video, which was, let's see, this is another video from the video series, The Machine That Changed the World, which was produced by WGBH Television in cooperation with British Broadcasting Corporation, and it was aired on PBS a few years ago, I think. I'm going to show you a video describing the NetTalk neural network, which was developed by Terry Sonowski, who's a researcher. So NetTalk was one of the major milestones in the history of neural networks. And the specific application is getting a neural network to read text. So in other words, can you show, piece of English to a computer and have a computer read, so verbally produce sounds that correspond to reading out reading out the text. And it turned out in the history of AI and the history of machine learning, this video creates a lot of excitement about neural networks and about machine learning. Part of the reason was that Terry Sonowski, had the foresight to choose to use in his video a childlike voice talking about visiting your grandmother's house and so on. You see it in a second, and so this really created the impression of the neural network being like a young child learning how to speak and talking about going to their grandmothers and so on. So this actually helped generate a lot of excitement within academia and outside academia on neural networks, sort of early in the history of neural networks. Let me just go ahead and show you the video.
You're going to hear first what the network sounds like at the very beginning of the training. And it won't sound like words, but it'll sound like attempts that will get better and better with time.
The network takes the letters, say the phrase grandmother's house, and makes a random attempt at pronouncing it.
Grandmother's house.
The phonetic difference between the guess and the right pronunciation is sent back through the network.
I'd run with a dog. Grandmother's house.
By adjusting the connection strengths after each attempt, the net slowly improves.
And finally, after letting it train overnight, the next morning it sounds like this.
Grandmother's house. I like to go to my grandmother's house. Well, because she gives us candy. Well,
NetTalk understands nothing about the language. It is simply associating letters with sounds.
All right. So at the time this was done, this is I think this is an amazing piece of work. I should say, today there are other text-to-speech systems that work better than what you just saw, and I guess you also appreciate this.